In a eutectic material, one that has lamellar phases that are interlocking, each phase can be made really thin. So you can imagine if I shine light on this lamellar structure, the photogenerated carriers only have to travel a really short distance to each interface in order to be collected and for the solar cell to provide electric power. That allows you to use really impure metallurgical grade materials. And so contrast, for a typical commercial cell, you need really pure materials because the carriers have to travel really long distances in order to get collected. So that's really the advantage of a eutectic solar cell.
My name is Craig Shaner, and I actually got into material science in the first place because of Batman. I went to see the movie Batman Begins in theaters when I was in high school, and there's a scene where Batman gets his new cape, and it flows like a regular fabric, but if you apply an electrical current to it, it springs back into a rigid shape. And I was like, that's the coolest thing I've ever heard of. So I went home right after the movie, and I looked it up, and I found out that no, it was not real, not yet, but there were people working on it, and that those people were involved in material science. And that made me want to be a material scientist.
Actually teaching 220 with John Halloran, and we were on the eutectic phase diagram part of the class. And I saw these eutectic phase diagrams in metal systems, and they're pretty striking. There's these beautiful interlocking phases of two different metals. And I went back after that class, didn't kind of think about it for the rest of the day, but at night I was in my office just thinking, well, I wonder if you could do this with semiconductors. And so went on to the database on the library's website, looked at a bunch of binary phase systems, and all of a sudden I found the magnesium silicon system. And there's this eutectic right at 57% weight silicon, and underneath it are two phases. One is magnesium silicide and one silicon. Turns out you can make a lamellae, a nice interlocking pattern of those two phases. Turns out magnesium silicide is a semiconductor, as I researched a little bit more. And then it turns out you can also dope the two, one P and one N, using one impurity, which is aluminum. So you could realistically make a PN heterojunction out of this, and got really excited and got the ball rolling.
Somebody who is taking introductory material science really needs to know phase diagrams, because none of the work that I'm doing right now would exist without them. They're the basis for all of what I'm doing here. Without them, it would at the very least would take a lot longer to get started, because phase diagrams, we can just go look it up, see the interactions between two materials, see what potential properties we can get out of it. And that's what material science is all about. It's about relating the structure of a material to its properties.
So this is a SEM image, a eutectic in the magnesium silicon system. The dark regions here are magnesium silicide, and the lighter regions are silicon. And this is basically the basis of our new solar cell that we've invented that will potentially allow us to make them at really low cost and with high efficiency.
What's exciting about my research is that, in my opinion, alternate energy is basically the future of science. We're slowly running out of oil and all that, and we're going to need to come up with some new ways to generate electricity, because we're consuming more and more and more every year. And I think that solar power in particular, which is what I'm working on, is going to be a huge thing in the near future. And a lot of what I'm doing is focused on ways to make it cheaper and more accessible to the everyday person. So it's really cool that in 15 years I could be driving down the street and see something that I worked on the roof of one of my neighbors.
Phase diagrams are really important. It's absolutely critical for students to understand phase diagrams. This project would have never got off the ground had I not really understood what a phase diagram is, how to make use of it. And it's not just having an appreciation of a phase diagram, but really understanding all the different components. For example, what is the eutectic point? And what does the alpha phase mean? These things are really critical if you want to do anything new or innovative. Now, the field has been around for a long time. I mean, phase diagrams are well understood, but this just kind of goes to show you that you can still come up with new ideas, as long as you really have a good understanding and knowledge of the phase diagram.